Okay. This next chapter deals with the structure of crystalline solids. Yeah, actually, we had discussed a little bit in the first hour, first session in the morning, yeah, in the early morning, about the crystalline structure. So this is the higher level structure after the atomic bonding structure. So we will discuss how actually do atoms assemble into solid structure. Especially here, we will focus on metals. Yeah. Then we will discuss how the density of the material depend on the structure, on this crystalline structure. And when do materials property vary with the sample? It has the part of the sample in the orientation. Yeah. Okay, so we have discussed this, yeah, about energy, the bonding energy, which is basically a function of the distance between the atoms. Yeah, so when they are exactly at the bottom of this energy slope, energy valley, then it means they are in the most stable condition. Yeah, and usually this occurs when the atoms are structured in a dense ordered packing like this. When it is still has some spaces, yeah, non-dense, then it is still in the this region, yeah, or in this region where uh, binding the attraction force may still occurs to make it more stable condition. Only when they are already in the middle in this region of the energy distance plot, then it usually is more stable, the most stable configuration or structure of the material. When you push further, for example, when you compress, of course, the distance gets smaller, then the repulsive forces start to occur. So dense ordered pack structures tend to have lower energies. Lower energies here means that more stable energy. So in crystalline materials, atom pack in periodic three-dimensional array, as I have explained also in the previous chapter. Yeah? And that is why crystalline material are usually more stable. They have larger melting temperature, they have smaller thermal expansion coefficient, etc. Typically, this occurs with crystalline materials occurs with metals, and many of the ceramics are also in the crystalline state, and some of the polymer. So this is example of crystalline silicon dioxide. So silicon dioxide is quartz, yeah, quartz. The name this is basically equal to quartz. Yeah? But silicon dioxide can occur in many different crystalline structure. It could be occur in quartz when it is in amorphous state. It occurs like this one. Yeah, this is non-crystalline silicon, or we call it as amorphous. Then it becomes the glass structure. Yeah, the glass that we use that is transparent. It is usually in the amorphous state of silicon dioxide. So in non-crystalline material, the atoms they do not have periodic packing. So like this, it's more random. The chemical bonding is the same. Yeah, the chemical bonding between this crystalline silicon dioxide and non-crystalline dioxide, they are the same. Yeah, one silicon binds to two oxygen. Yeah, most probably in the covalent binding because I think they have almost similar electronegativity number. Non-crystalline materials occurs when for complex structure or when the structure is cooled rapidly. So after in the molten state, yeah, like uh, Ezra asked during the first session or second session, I forgot. Usually we start from melting material, molten state of the material in the liquid state, and we cool down to make the material solidify. When you cool down very rapidly, yeah, in the molten state, it is the structure is not in periodic packing, not ordered structure. The liquid because it is liquid. The molecules they can travel independently of the other. So when you cool rapidly, they become solid. They solidify, but still there are some spaces between the molecules, like the one shown here. So the order of the packing is not that high. So if you want to have ordered crystalline structure with less imperfection, usually you will cool down slowly. Yeah. Okay. So we already mentioned about crystal system, yeah, in the previous slide, and each crystal system consists of a single unit cell. This is the smallest repetitive volume, which contains the complete lattice pattern of a crystal. Yeah, the length parameter are three based on the three axes x, y, z, and the x is called as the a, the constant lattice constant a in the x direction, x-axis direction. Lattice constant b, lattice length b, is the length in the y direction for a single unit cell, and lattice constant c is the length in the z-axis direction for that unit cell. And the angle between a and b is gamma. Okay, between b and c is alpha. Between the C and A is the beta. Okay, we have 7 crystal system and 14 crystal lattices. Okay. And we have discussed this in the previous slide. Okay, we have cubic 7 crystal system, cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. So with cubic, the three crystal lattice are the same. A equal to B equal to C. The angles are also the same and equal to 90 degrees. Alpha equals beta equals gamma equals to 90 degrees. Tetragonal, you have three axes at the right angles. Two of the axes are equal. A equals to B, but is not equal to C. Alpha equals beta equals gamma equals 90 degrees, etc. for all the other, yeah, with crystal system with each of these different characteristic of axial length and interaxial angles. For cubic, we have three different lattices. Simple cubic, yeah. This simple cubic means that the atoms only fill the corners of the cubic. We have body center cubic, where the atoms fill the corner, but as well as at the center of the cubic. We have face center cubic, where the atoms fill in the corners of the lattice plus the center of each of the side or yeah, of the cube. Then we have for tetragonal we have two space lattices, simple tetragonal, atoms only fill in the corners of the tetragonal space, and body center tetragonal plus the center of the tetragonal structure. Orthorhombic has the most lattice system, four lattice system, simple orthorhombic, yeah, only at the corners, body centered orthorhombic at the corner plus one at the center, base center orthorhombic. This one is at the corners as well as at the bottom and top side of the orthorhombic structure. Then we have face center orthorhombic. This is similar to face center cubic. Rhombohedral has only one lattice structure, simple rhombohedral. Hexagonal has only simple hexagonal. Monoclinic has two, simple monoclinic and base center monoclinic. And triclinic has only one, simple triclinic. So this picture shows the 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The 14 standard unit cell from the 7 crystal system. Yeah, from the 7 crystal system. So from cubic, we have here simple cubic system. Okay, this is simple cubic system. This is face center cubic. This is body center cubic. For orthorhombic here, yeah, the angle, the interaxial angle is 90 degree, but we have A equals to B, not equal to C. Is not equals to B, not equal to C. So A, B, C could be different. So we have simple orthorhombic. We have base center orthorhombic, face center orthorhombic, and body center orthorhombic. Then we have tetragonal. A equal to B and is not equal to C. The angles, interaction angle are 90 degree. Simple, tetragonal, body center, tetragonal. Then we have hexagonal, simple hexagonal. We have rhombohedral. Rhombohedral is A equal to B equal to C, but the interaction angle are the same but not equal to 90 degrees. Simple rhombohedral. We have monoclinic too, simple monoclinic and base-centered monoclinic. Yeah. This one. For triclinic, we have only simple triclinic. Okay. So in the cubic system, yeah, this one I have just explained. So first, the atom position is usually indicated as coordinate. As coordinate, for example, here at the origin is coordinate is 0, 0, 0 in parentheses and with comma between the number. Then here at the z axis at 1 at the c equals to equal to c, the crystal lattice 0, 0, 1. Here at this edge 1, 1, 1. When it is at the center, it is half, 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 etc. So atom positions in unit cell are located by using unit distances. One single unit equals to the parameter of that crystal lattices. Yeah, so in the case of cubic, then A equals to B equals to C, okay, or just A. So in direction we have learned a little bit in the previous chapter. So when we have direction is basically a factor that connects two lattice point. Usually, then the origin we put at the origin of the coordinate. So how to express direction in the notation, the correct notation in the material science? First, find the magnitude of each x, y, z. They have to be made into integer. The positive and negative direction are not the same. Yeah. So, for example, 100 and 200 actually have the same direction. For example, here, the first one is from the origin to a single unit length. Okay, so this is equal to the x-axis is 1, the y-axis is 0, z-axis is 0. So 100. This one from O to S is 1, 1, 0. Okay, in straight bracket, in rectangular bracket. From O to the H, the T here, 1, 1, 1. From O to M here, X is 1. Okay, let's just try to solve it. So X here is 1, this is half, and the Y and the Z is 0. So 1, half, and 0. The direction should be integer, so we have to multiply by 2. This becomes 2, 1, and 0. Then we enclose in straight bracket. From here, now the origin is put here, and then it goes to this direction. So X is -1, Y is also -1, the Z is 0. Okay, so this is already in integer, but then we put in bracket, the minus become over bar. Okay, become this bar. 1 over bar, 1 over bar, 0. Okay. Okay, then we have also learned about indicating or expressing plane in a unit cell. Okay, so we have here a plane. How to identify? First, choose a plane that does not pass the origin. Determine the intercepts, the intercept of that plane in each x, y, z axis. Then make a reciprocal. So you inverse the number, clear the fraction, determine the smallest set of whole number. So for example, this plane intersect x at 1, intercept y at infinity, right? Intercept z also at infinity. So you form the reciprocal. So this is 1 over 1, 1 over infinity, 1 over infinity. This has become 1, 0, 0. You put under parenthesis. This one, intercept x at coordinate 1. Intercept y also at coordinate 1. intercept z at infinity, because basically it does not intercept z-axis. Then put in reciprocal 1 over 1, 1 over 1, 1 over infinity, 1, 1, 0. Like this plane intercept x at 1, intercept y at 1, intercept z also at 1. The reciprocals are 1, 1, 1 as well. Immediately you put under parentheses. So far, is it quite clear? Yeah, I hope quite clear. For example, determine the Miller indexes of this plane. So this intercept at 1/3, yeah, the x-axis at 1/3, the y-axis at half, at 2/3, yeah, the z-axis at 1. So you make the reciprocal 3, 3 over 2, and 1. This still contain fraction, so you have to make them integer. Multiply y 2. So this becomes 6, 3, 2. This is the Miller indexes of this plane. Okay. Now, if I make you this, can you draw the plane? Okay, let's have a practice first for about 5 minutes. Oh, what time is it? So we have only about 10 more minutes. So let's use the same group. Yeah, let's use the same group. Group 1. Who is group 1 just now? Ezra and Grace. Draw 2, 1, 2 plane. Group 2, Andy and Anjali. Draw this plane. Okay. Okay, so I give you 2, 1, 2 and 3, 1, 3, 1, 3. Let's make another. Okay, you have you recorded. If you noted, let's make another breakout room. Opens all room. Yeah. Ezra to. Yeah, group 1 is Ezra. Yeah. Okay. Please join. Okay, just draw in a single slide, yeah, in a single PowerPoint slide. 2, 1, 2. Okay. I will move. Okay, draw in single slide the plane 3, 1, 3. Okay.
So as we can see here, is if it is 1 over half, then the answer will be 2. So yeah, 2, 1, and 2. So the last one is to determine the intercept. So for the intercept, it is only the value of this one, the denominator.
Yes, yes.
So it is simply half, 1, and half.
Okay.
I forgot this is A, B, C.
Okay.
The A is in for the x-axis, the B is the y-axis, and the C is the z-axis.
Yes.
So since the intercepts at the A is half, so here this is our first point, and second is the since the intercept is 1 at B, so our second point will be here, which is 1. And the third intercept is half. So at the z-axis, the point will be here, half of the z. So this is our plane from the 2, 1, 2.
Okay, yes, this is correct. Okay, very good. Okay, thank you.
Thank you, sir.
Let's do it. Group 2 now.
Okay.
Group 2, Andy and Anjali. 3, 1, 3.
Saya
So,
gambar kotak ya Pak. Bentar ya Pak.
you can draw using the Zoom's whiteboard if you want.
Oh, gambar ini aja di sini.
Ya, boleh.
Udah saya gambar sih sebenarnya Pak, pakai tangan. Cuma kita pakai Zoom whiteboard aja lah ya.
Ya.
Anjeli ya.
Ini kalau bisa.
Gambarnya gimana ya?
Kan gambar straight line aja. If you are using the whiteboard, you can use the line. You can draw line. It's quite easy. Using the draw, not curve, but line. Yes. First, draw the unit cell. The unit cell, the one. You draw the box.
Ini X, Y, Z.
Kenapa Angel?
Ada lagi. Dan
Nah, Angel mana?
Hilang koneksi kayaknya Pak.
Hilang koneksi ya.
Kita pakai warna kuning saja lah ya.
Oke.
Aduh.
Draw the box first, the unit box.
Ya udahlah biru aja lah.
Biru aja nggak apa-apa, satu warna juga nggak apa-apa. One color is okay.
Ya gampang juga ya gambarnya di sini.
Susah banget kayaknya gambar box.
Iya Pak. Aduh.
There's also box there in the whiteboard ya, directly apa square and rectangle.
Wah, nanggung sih Pak. Jadi
Like this. Nah, like that. Straightforward.
Okay, so
where is 313?
313 berarti X-nya 3 right here, and Y-nya 1. Ya kira-kira seginilah ya. And then Z-nya juga 3.
Where is Angeli is gone kan?
Tada.
Yeah, let's check ya. So it means let's now going the reverse direction. Yeah. Your plane intercept the x-axis at coordinate 1, right? 1, 0, 0. And intercept the y-axis at coordinate. This is what is this coordinate? This is 1/3. 1/3, yeah.
Oh ya.
1/3. Okay, so comma 0. So this one at 0, 0, 1. Okay. So intercept at x is at 1. Intercept at y-axis is 1/3. Intercept at the z-axis at 1. So let's see the reciprocal is 1/1, 1/1/3, and 1/1, or 1, 3, 1. So the plane is 1, 3, 1, not 3, 1, 3.
What?
Using this. Okay, can you make revision?
Oh, kebalik ya.
Yeah, okay. Since time is up, so please later I will put in the assignment, upload your presentation, yeah, Andy and Angeli for this, yeah. So this first answer from the drawn by Andy is the wrong Miller plane, okay. What you want is 313, yeah, not 131. Okay, plus please fill in the online attendance for the third session, which is 1021. The OTP is 1021. Okay, so please fill in the online attendance week 2, session 3. I will put the